My name is Fred Mitchell, and I am in the process of creating the MGS fourth generation, Mitchell Gravity Set fourth generation. Um, and this is rather a complicated way to generate fractals. And it's based off of Newtonian gravitation and the errors that accumulate in Eulerian integration. They result in very interesting fractals. This is the fourth time I've done this over the past 3 decades. Has it been that long? Yes, it has been that long. Um, the first time I did this was when I was at Commodore. Remember Commodore back in the late 80s, early 90s? I was there for 5 years up until their demise. Well, while I was there, I was doing a lot of graphics programming and whatnot, and so this idea popped up of doing fractals from the equations of Newtonian gravitation. Um, a paper for this, my little write up for this is can be found below in the links. So, the initial version was in 2D. It was running on the Amiga, and it was rather slow, but I did create some stunning images of what looked like to be. I dubbed them gravity creatures. All right. But it took a long time to generate those images because this is a rather compute intensive operation running on the 68030 back then, which by today's standards is doggedly slow. But back then it was closer to state of the art as far as speed for, you know, user type CPUs go. Anyway, spinning forward a few years, I rewrote this algorithm again in Visual C++ using the MFC classes. That so I generated images from that again, and then MFC changed their framework, and that program no longer compiled. And that was circa 1994, 5, somewhere around there. And then afterwards, I did it a third time, and this time on Linux, using the Qt framework, circa 2000. And that was also 2D. And generated some more images with that. And Qt changed their framework, and I was unable to recompile that code anymore. Unfortunately, the code for all these prior instances have been lost to time. This was back in the day before we had GitHub, and I had them on hard drives that long since have died, or I've lost the ability to be able to read anymore, just because the technology has shifted over time. So now this is the fourth generation, and if you're into fractal images, you have noticed that a lot of them have gone 3D, three-dimensional, even four-dimensional. But NGS has been two-dimensional up until now, just because it's already compute intensive for two-dimensional images. But now with today's multi-core and GPU systems, we can do much better. So now this will be 3D. Now what you see here on the screen is not actually MGS per se, it's the configuration screen for MGS. Alright. And it's rather intense because here you have a complete 3D visualization of the configuration. So this isn't even MGS. The part that actually does the actual rendering has yet to be written. I will be doing that shortly. But as you can tell, it'll be a 3D rendering, so it will be non-trivial to accomplish. And I'll be doing it using either isolinear surfaces or volumetric rendering, or maybe both. I haven't quite decided yet. But in the meantime, you know, while playing with this, I came up with some surprising things. So, without further ado, let's get right into it. So, I'm going to just hit the simulation. Okay. So now you see a cube of arrows. Now, for me to describe what I have here is going to be rather tricky, but I'll try to get to it anyway. Okay. Now, I am violating physics a little bit, but I'll get to that. The arrows point in the general direction of the velocity vector that they're all tracing. And you can see weird things going on, which may not make sense to you, but will. Okay, so we got 4 stars here. I'm sorry, 6 stars arranged in an octahedron, the vertices of an octahedron. Now, okay, so one violation of physics here is that these stars are fixed point. Because I'm generating a fractal, I don't want the stars themselves to move. I want the free point masses to move. All these arrows you see all over the place, those are what I want to move. The stars themselves are fixed point. So that, you know, we're more interested in what the free point masses are doing. You know, the little arrows. Now I can freeze the simulation, so I can show you what this has done so far. Now, you might be thinking, well, it seems like the arrows, or the free point masses, are interacting with some of the stars and being repelled from the others. Well, that's by design in this particular case, because yet again, a violation of physics, but you know, with math, anything is possible. Some of these stars have negative masses, mainly this star here. You can see this is star 2, and it's got a negative mass of 20,000. And this star down here, star 1, also has a negative mass of 20,000. Okay. The rest of the stars, as you can see, have positive masses. Now, for this particular configuration, the total number, the sum total of all the masses is 0. Okay? So the negative masses, they sum up to negative 4,000. And these 4 masses here all sum up to 40,000, not 4,000. So you got negative 4,000 with these 2 guys, plus a positive 40,000 with those 4 guys, which is a net of 0. So at, quote, infinite distance, there should be no force. Well, we're not at infinite distance, are we? Of course not. So this is just some of the dynamics that I like playing around with. Okay. Over here, you can see that I can make the gravitational constant anything I want. This is delta time, so as this simulation goes on, the delta time is used to control the jumps in the Eulerian integration from the next instant from one instance to the next. Iteration limit, this is how long it takes for a free point mass to escape from the system, or how many iterations the free point mass is taken, okay, before, up until it escapes from the gravitational system. Right now, this isn't being used for this, for the visualization here, because this isn't the MGS itself. The escape radius, similarly, is not being used, but that just represents how far out the free point masses can go before we consider it having escaped from the system. All right. So, and then we got simulation speed, which isn't wired in yet, but that controls how fast the simulation runs. Okay. So with that, let's play around with this. Let's restart this. Okay. And if we zoom out, we can see the cubal arrangement of the arrows. You can also tell that they're pointing in different directions, tracing out basically the gravitational fields that, you know, are affecting them. And they're also moving in the direction of the field. So because the negative mass is here and here, the top and bottom, they're generating this bell kind of shape. You know, the arrows are being repelled from this area and this area, and being attracted to the positive masses here. The four positive masses in the middle. Okay, so we can zoom in and see more what each individual arrows are doing. There is no collision detection because, like I said, that's not important for what this is doing. This is just to give me an indication of the dynamics of the free point masses, so I can better plan in generating the actual gravity set fractal. And you can tell it's pretty intense. This in and of its own right is you know, fairly interesting how these arrows are moving. Now, you may see some weird phenomena like this here. You got these two arrows in the middle just bouncing between the negative mass stars. With this type of symmetric arrangement, you'll see things like that quite a bit. And there's also an artifact here where the arrows are not pointing in the direction of motion like they're supposed to. So I'm using quaternions to aim the arrows in the direction of the velocity vector. So there's some weirdness in the math for these two, but I don't care because, like I said, this isn't the point of this program. You can see some of the arrows doing funky things, interacting with the positive mass stars, whipping around them, almost in orbit, but very chaotic orbits. And then further out, you can get a sense of the aggregate motion of all these arrows. Now, if you watch these long enough, they don't seem like masses floating through space. Oh, and did you see that? Those are arrows that are being ejected from the system at high velocity because these stars are basically singularities. So because this is Eulerian integration, there's a lot of error, especially near the singularity. So any free point mass getting that close to the singularity will, just from going from one jump to the next, will pick up so much momentum and speed. Like I said, this isn't supposed to mirror physics exactly. We'll pick up so much momentum and speed that it'll just be ejected from the entire system. And those are the ones you see flying off at high velocity. And, well, I'm just kind of enjoying the power of cute here. There's some more arrows that are ejected. You can see them are occasionally just being ejected from the system. This is the power of Qt that allowed me to do this simulation very easily as far as the graphics go. So I mainly just had to focus on the actual math of the system and of the quaternions to control the orientation of the arrows. You just saw that arrow just re-aim itself. Okay, so let's play with some of the parameters. So let's reset the FPMs, the free point masses. Okay. But now, you can see the formation of everything. But now we want to do something different. Let's stop the simulation. We don't really have to stop it, but let's change the gravitational constant to be negative. Okay. Now you might be wondering, well, obviously in real physics there's no such thing as a negative gravitational constant. In fact, the gravitational constant by definition, it never changes because it's constant. In actuality, it may actually change, but that's besides the point. We don't want to get into a big, deep cosmological discussion here. I'm just staying with this. As tempted as I am to go that route. But at any rate, so we stopped the simulation. We made the gravitational constant negative. So what will happen there? You can think about that for a moment, but I'll just tell you. Stop the video if you want to think what's going to happen in this particular situation. Okay, I'm going to tell you. What will happen is that the negative masses will behave like positive masses, and the positive masses here will start behaving like negative masses. So it's almost as though we flip signs, except there's some gotchas there. It's a little stranger than that, and I think it's just more fun to watch and get into an explanation of the details. So let's restart, and now we're working with a negative gravitational constant. Nothing else has changed, and we'll start simulation. You see a lot of these arrows are pointing away from the system, except these up here are being sucked in. They're pointing towards the negative masses, which are now behaving like positive masses because we flipped the sign of the gravitational constant. And you can see these arrows doing a really strange orbit. You can see entire groups of arrows coming in and being sucked in. And everything is being repelled from the four positive masses, which are now behaving as though they're negative masses. So we have this donut or toroidal vacuity surrounding the stars. which just keeps expanding in its nature. And the flow is basically away from the center and down and up and into, you know, the top and bottom stars, as you can see. You can zoom in and watch some of the dynamics. Kind of fun, huh? And again here we got this weirdness where we've got, in this case, 4 FPMs bouncing between the negative mass stars. Well, like I said, they're positive mass, but they're behaving like negative mass stars, and they're just bouncing back and forth between them. Now, in this case, the arrows are behaving themselves as far as pointing in the direction of motion. All right. And up here, you have arrows that seem to be swimming around. Oh, you can see some that are being ejected from the system at high speed. And others that are just swimming around the top and bottom stars. You almost could probably see this like some weird fish. You know, it's kind of like watching fish swim around a fish tank. All right. With a lot of arrows, it tends to get a little cluttered, so let's restart this with a small number of arrows. This is the smallest number, 4, which basically says there's a cube 4 on a side. If we were to do that again, so it doesn't look like 4 on the side, does it? It's like 3, but that's besides the point. Why it's not exactly 4? I think the 4 arrows are outside of the viewing area, the outside arrows, but we don't really care about that. So now we can see more of what the arrows are doing without all the clutter. It'd be interesting to do breadcrumbs with some of these arrows, because they are tracing out interesting shapes. You see how these 4 arrows, they swoop out, swoop back to the top, and then we'll see these are chaotic orbits, so they're not exactly stable. So you just saw a bunch of arrows shoot off at high speed, it being ejected from the system. So the ones that remain, they come down, attracted to the top and bottom masses, and because of the negative fields here, they're being repelled right back the way they came from, upwards. All right. So now let's try something else. Let's go to a rather high setting. Okay, so we got 13 arrows on a side here, so all cubed. Now we can see the formation of that toroid or that donut vacuity around the star system. And we can see a flow where the FPMs are going up, around, and down into or up into the top and bottom positive gravitational attractions. You can rotate around the whole thing, and you can see an intricate dance of arrows in bunches even. So we're looking at it from the quote bottom. And we can see a lot of complex things going on. Arrows flowing in, flowing out. Some arrows doing some weird things. Arrows being ejected at high speed. So now we've got two lobes, one at the top, one at the bottom. If we could see beyond the confines of this viewing area, we would see a rather big torus surrounding these stars, possibly expanding. And I find that you don't get a real sense of what's going on unless you actually rotate the image or rotate the field. Okay, so now let's put this back to a positive gravitational constant while it's running, which then immediately flips the sense of gravitation of the stars. And so all the arrows now start doing something different. And of course, if we were to do this from the beginning, now we got a positive gravitational constant. And we can see what would happen here. So now the top and bottom stars actually have a negative gravitational field because they're negative masses again. Well, they're because yeah, and then the four stars around the ring of this octahedron ring, they're positive again. So now you basically see, you know, the top and bottom areas becoming vacuous of 3-point masses. And then the flow is going down and around and into the center here. And you can see these intricate dances going on. There's interesting things going on in the middle of the star system here. Now, what may have caught your eye is that we have various different, we have all the 5 Platonic solids represented up here. So we got the tetrahedron. Okay. And I'm going to change just a smaller. Now when I reset this, all the masses of the stars are reset to defaults. So now we have all positive mass stars, each one mass of 10,000. Okay. And you can see all the arrows being attracted in and interacting. In quite a chaotic fashion. In an arrangement that roughly reflects the arrangement of the masses themselves. And we'll just go through each of them. Octahedron. Well, now we're back to the octahedron, but they all have the same masses. Okay. They all have 10,000. That's the default mass. Now you can see jets streaming out of the star system at various angles. There's a lot of complex things going on. In the center even. Alright, let's go to the cube and reset the FPMs. Again, you can see, it might be tough to see, but I can see it, but then I know what to look for. Subtle arrangement of the arrows that reflect the geometric arrangement of the stars, which is not to be unexpected. Okay, let's go to the dodecahedron. Things tend to get more chaotic and harder to see patterns, especially with this many stars. But even here, there's interesting things going on. Okay, let's go to the icosahedron and reset. It's like a rain of arrows. try to icosahedron with far fewer arrows. You can see one stuck at the exact center of the star system. It's being attracted to all the masses equally, and it just can't break out. You can think of it as a type of Lagrange point. If you know, Lagrange point for fixed point stars. Yeah, it's just stuck there. It won't go anywhere. Now, to prove that this is not a bug in a system, but is actually a Lagrange point of sorts. And the Lagrange points of fixed point stars don't work the same way as they do in actuality, because, well, these stars are stationary. They're not moving. So that changes the whole character of the thing. But if we were to modify, we can modify masses of individual stars, obviously. So if we were to modify this mass, even by a little bit, let's try something really small. I'll modify it by 1. Now, 1 is not enough to upset it. Okay, let's do that. So we upped it by 11, that one particular star. It's still too small to do anything. Let's do it by 111. Now, that was enough to kind of dislodge this point from being trapped. And now it's gone. So we made all the masses the same again. So you might ask, what happens if we make one mass much higher than the others? Let's say this mass here, the star here, let's make it 10 times the mass of all the others. So now it's 100,000. And now you just notice there's a lot of FPMs popping out from beyond the viewing area, which I will call the Oort cloud. Okay, those floating around outside the viewing area, and now they're being pulled in, particularly because we have a higher mass. Now, let's restart the simulation again with the higher mass. And now you notice distributions. And star 12, that has a higher mass. So you notice somewhat. Let's do it again. You notice a higher number of FPMs in the area of the higher mass star, but it shifts. Yeah. Let's try with a few more points. Let's go with 9. Yeah, you can see jets forming above the higher mass star, star 12. Okay, let's make star 12 negative in mass. See what happens. Already it changes the dynamics, and when we start flowing away, let's restart it. And as you see, we get that, kind of magnetic field looking arrangement of the 3-point masses as they're repelled from the negative mass star, which is pretty intense, and then they are attracted to all the positive mass stars below. Okay, so now we've played around enough with that, so let's go to the cube. We're going to have additional fun with doing the impossible physics here. So now, we're back here at the cube. And now, let's make delta t, right now is 0.1. So now let's make it 0.01, which will result in an apparent slowdown of everything because it's just doing more computation at a finer grain of level. So it hasn't really slowed down, it's just the steps are constant, and you know, the software wouldn't be able to keep up very well in the simulation. So they appear to be moving slower, and the integration is more accurate. So you'll actually see less points being flung off at high speed. Well, you still will see it, but there'll be less of them. So now, let's do this. And it's moving so slow you can barely see. So let's make delta t, oh, you see some stuff. Let's make delta t 0.05. Okay. So now it speeds things up. Let's restart. And we can see how the arrows are being sucked in. Now, I'm going to make delta t negative. What do you think happened? I've made it negative. So it's almost like a time reversal. You see the cube structure of the FPMs reforming. So it's not a perfect reversal, right? And then you just notice all the arrows are pointing in the opposite direction. So we reverse time basically, essentially. So the arrows are pointing away from their, you know, velocity vector, because time is running in reverse. You see all these arrows moving backwards. Let's make it positive again. Now that I've made it positive, you can see that the original cube arrangement of the FPMs is trying to reform. It's not perfect, because errors have built up in the system, but that's okay. And then they reverse, and they're going in again. So you can see with this system that anything is possible.
Yeah. What I see.
And that voice that you hear is my wife being annoying because she knows I'm making a recording here. She insists on being annoying anyway. But I love her. So, that's it, folks. Let's just let you see one more thing. But I hope this gives you an idea of the fidelity of the settings in this configuration screen that is possible for the gravity set. Thank you for viewing, and
I didn't do
I'll
that.
do a another video once I have the actual gravity set renderings done, and that's going to be even more amazing, I think. So thank you for watching, and have a good day.